All right, let's dive right into this explainer. Today, we're literally looking under the hood of modern aviation to unpack the hidden physics of flight. We're going to be digging into a truly fascinating piece of research from the Aerospace Research Letters. This study is awesome because it breaks down exactly how, and more importantly, why, helicopter engines behave the way they do when they're pushed right to their thermodynamic limits.
It's a fundamental mystery of aviation, isn't it? Have you ever wondered why a machine that can effortlessly lift actual tons of weight at sea level suddenly starts to struggle as it climbs higher? Well, to solve this puzzle, we actually need to track down an invisible energy thief hiding deep inside the engine. You see, it's not just about the changing air outside the aircraft, it's really about the dynamic shifts in energy happening inside it.
So, here's our roadmap for this breakdown. We're going to start wide with the real-world physical challenge helicopters face, zoom right into the engine's mechanics, and then untangle the thermodynamic showdown between energy and exergy. After that, we'll reveal the actual altitude penalty, pinpoint our energy thief, and finally, look at what all of this means for the future of flight.
Okay, step 1. Let's start with the physical problem pilots are dealing with every single day when they take to the skies.
As a helicopter climbs into thinner air, and for this specific study, we're looking right at that 0 to 900 meter range under standard atmospheric conditions, the engine literally starts struggling to breathe. Because air density drops as you go up, the actual mass flow rate of air entering the intake drops too. Think of it like trying to run a sprint at the top of a mountain. Your lungs are pumping furiously, working just as hard as always, but there's just less oxygen in every single breath to fuel your muscles. For the helicopter, this exact aerodynamic reality results in a frustrating, unavoidable net power loss.
To really grasp this struggle, we've got to get up close and personal with the machinery itself.
Behold the beating heart of our subject, the Augusta A119 Koala helicopter's engine. This beautifully engineered beast is the Pratt & Whitney Canada PT6B37A turboshaft engine, and man, it is a brilliantly complex piece of tech. It rapidly compresses incoming atmospheric air, mixes it with aviation fuel, and then converts those highly energized expanding gases through a multi-stage turbine to drive the rotor system. Basically, it's a highly controlled continuous explosion that bravely defies gravity to keep you in the air.
The numbers behind it are absolutely staggering. This engine boasts a thermodynamic power rating of 1,000 shaft horsepower and spins its output shaft at a dizzying 4,373 revolutions per minute. It's built to lift the Augusta A119, which rocks a maximum takeoff weight of 2,850 kilograms. That is nearly 3 tons of complex machinery, fuel, and passengers. But despite all this raw, immense power, even this mechanical marvel is completely vulnerable to the altitude penalty we just talked about.
So why is it vulnerable? To figure that out, we need to pivot our perspective a bit and introduce a high-level engineering concept that goes way beyond basic performance metrics.
You see, conventional energy analysis just isn't enough to find the real leaks in a system like this. Energy analysis relies on the first law of thermodynamics, the classic rule that energy cannot be created or destroyed, only transformed. That's great for figuring out overall thermal efficiency and raw fuel burn, but it doesn't give us the whole story. To see the full picture, we have to compare it to exergy analysis. Exergy brings in the second law of thermodynamics, dealing with entropy and the actual quality of the energy. This is what lets us identify precisely where usable energy is being lost inside the engine's intricate stages.
The crucial takeaway is this definition right here. Exergy isn't just the total energy you're dumping into a system. It measures the usable energy. It relentlessly tracks down exactly where the potential for actual mechanical work is destroyed by irreversibilities. We're talking intense friction, rapid heat loss, or extreme chemical imbalances. By using exergy, engineers aren't just asking, how much energy did we use? They're asking the much more important question, how much of this energy did we waste and exactly which part of the engine wasted it?
All right. Armed with exergy as our analytical tool, let's look at the hard data extracted from that simulated 900-meter climb.
Down at sea level, this engine is an absolute powerhouse. It pumps out a massive 712.3 kilowatts of shaft power, operating with an overall energy efficiency of around 26.2%. At this baseline, everything is humming along perfectly because the air feeding the engine is nice, dense, and rich.
But take a look at what happens when we pull that helicopter up into the sky. Pushing to 900 meters triggers a harsh 9% drop in shaft power, along with a parallel 9% drop in thermal efficiency.
On top of that, specific fuel consumption actually goes up, and there's a noticeable spike in exergy destruction. Because the air is thinner, the engine is forced to work significantly harder, burning fuel far less efficiently just to maintain its baseline flight. If you're a pilot planning a heavy payload mission or a high-altitude rescue, a 9% power drop is a massive real-world constraint. You just can't ignore it.
Surprisingly, though, it isn't all doom and gloom. There's a genuinely fascinating silver lining to flying in that thinner air. The study shows that NOx, or nitrogen oxide emissions, actually decrease as altitude goes up. Why? Well, thinner air leads directly to lower combustion temperatures and a heavily reduced partial pressure of oxygen. Less oxygen means less nitrogen oxidation. So it's a slight, totally unintended environmental perk hidden right inside a pretty harsh mechanical performance penalty. Okay, so we know the raw power is vanishing, and we know exergy destruction is the culprit. But which specific part of the engine is to blame? Let's round up the usual suspects.
By zooming into the specific thermodynamic stations of the engine, literally mapping out the journey of the air from the intake compressor, pushing into the roaring combustion chamber, and finally blasting out through the power turbine, we can pinpoint exactly where our exergy is getting destroyed. The researchers used simulation software to carefully calculate the pressure, temperature, and mass flow rate at every single one of these physical checkpoints.
And through that exact mapping, boom, we found our thief. The research frames it perfectly, stating, chemical irreversibilities, entropy generation due to high flame temperatures, and pressure drops in the combustion process were among the key factors limiting overall efficiency. Turns out the combustion chamber and the exhaust are incredibly sensitive to atmospheric changes. The literature actually suggests that up to 74 to 80% of all exergy destruction happens right here in the combustion chamber. The sheer violence of mixing fuel and thin air at ultra-high temperatures generates massive entropy, permanently destroying the engine's potential for usable work.
Let's zoom back out for a second. We've gone super deep into the weeds here, but why does knowing all this microscopic, station-by-station thermodynamics actually matter for the future of aviation? It matters because this is the exact kind of foundational data that drives real innovation. By pinpointing these highly specific thermodynamic losses in existing engines, engineers aren't just guessing at improvements anymore. They have a precise mathematical map to work from. First, this data helps mitigate that 9% power drop by guiding new altitude-responsive hardware designs. Second, it optimizes fuel strategies for high-altitude missions. And third, it develops concrete parameter-based criteria for entirely new flight platforms.
Which leaves us with a truly fascinating thought to end on. As the global aviation industry pushes relentlessly for sustainability, could fixing this exact exergy destruction in today's gas turbines be the stepping stone we need? By deeply understanding how a combustion chamber wastes energy at 900 meters, engineers are laying the vital groundwork for the hybrid electric skies of tomorrow. We're looking at a future where traditional turbines might work seamlessly in tandem with advanced electric propulsion to finally, definitively defeat the altitude penalty. Now, how cool is that?